Hi students, in this lecture I am going to discuss a torque of a force. Let us see what is a torque and how that is defined. Let us consider a rigid body. This is now a rigid body. Applying force on that body. Suppose this is a force F bar acting at this point. Okay. You might have observed that. So when there is a door, imagine this is a door. This is now fixed at one end. Suppose here fixed. Okay. If we apply force normal to door at the other end, door will be opened. That means door is now rotated about this axis. I am repeating. If we apply force normal to door, normal to the plane of the door, somewhere here, it will rotate. Means door is opened. You just imagine applying same force at this point. Then door does not rotate, right? That means applying same force, but if we are changing the point of application, then this rotation also changes. So this is what we call torque. So torque is giving us a turning effect. So when we apply force normal to the door rotates, right? But if you apply force on this axis, then it does not rotate. So applying force at which point we apply is very important. Not only how much magnitude it is applied, it is also the location. So now we have to focus how to calculate now this torque. Okay. Let us take now this is one rigid body, applying force on that body. Now we are taking one origin, and with respect to that origin, position vector of this point. So this point means at which point force is acting. Okay. That is now R bar. So we have taken one origin. Okay. With respect to that, for this point means where force is acting, or this is the point of application of force. This is the position vector of that point. Then torque due to that force is defined as tau bar. This is now symbol tau bar equal to R bar cross F bar. It is R bar cross F. Okay. So in this R bar stands for position vector of the point where force is acting, or you can say position vector of the point of application of force. I am repeating, R bar is the position vector of the point of application of force. Now this is equal to F into R sine theta. So where theta is angle between R bar and F bar. So if these two are parallel or anti-parallel, there is no torque. Example is here. On the door, if you apply force parallel to the axis, this is now axis of rotation. If you apply parallel to axis or anti-parallel to axis, door does not rotate. So force must be, or you can say there must be a force component normal to this door. Then only door opens, right? So this is now F into R sine theta. Now in this, we have to focus direction of torque. It is nothing but a cross product. Therefore, direction is given by right hand thumb rule. So I'm writing here n cap, which gives unit vector along the direction of R bar cross F bar. And in this, R sine theta. So this is known as perpendicular distance. It is known as perpendicular distance, also known as arm length. It is known as arm length. And see how to get now this length. You just imagine one line passing through a point. Imagine a line passing through a point parallel to force. Okay, I'm taking a line passing through a point parallel to force. Then separation between these two lines. That is giving us perpendicular distance or sine theta, or you can say arm length. Okay, right. Let us now consider a uniform rod. So taking a uniform rod of length L placed on a smooth surface which is horizontal. Apply now two forces at the ends, both having same magnitude. So we are taking a uniform rod which is placed on a smooth surface which is horizontal. So initially rod was at rest. Okay. Now applying two forces at the ends parallel to surface means both forces are horizontal. Both forces are horizontal and they are anti-parallel. Okay. Then rod will rotate, but center of mass does not move because net force equal to 0. So these two forces now form one couple. So couple means two forces of same magnitude anti-parallel with some separation between them. They form couple. Okay. Now calculate torque. Suppose we want to calculate about center of mass of the rod. Now see carefully. Because of this force, about center of mass, torque will be anti-clockwise. About this point, if you apply force in this way, rod rotates anti-clockwise. So torque is anti-clockwise. So it is F into L by 2. Direction anti-clockwise. Next, because of this force, again rod rotates and sorry, not anti-clockwise, it is clockwise. Let me correct it. It is clockwise. When you apply force in this way, rod rotates clockwise. Because of this force also, it rotates clockwise. That means because of both the forces, torque is clockwise, F into L by 2. This also F into L by 2. See what is now net torque? It is 2F L by 2. That is F into L clockwise. So we have taken torque about center of mass. Now let us consider torque about one end. Then see what happens. Now this force is passing through this point. Therefore, for this one, because of this force, there is no torque. Okay. But because of this force, torque will be clockwise. And separation between from that point, it is equal to L. Means again torque equal to F into L clockwise. Okay. Okay. Do one more thing. Let us take a point on this line at some distance x from this end. Okay. Now I want to calculate torque about this point. Then see carefully. About this point, if you apply force like this, torque will be anti-clockwise. Students, you should be very careful here. We are calculating torque about this point. About this point, if you apply force in this way, torque will be anti-clockwise. So F into X, anti-clockwise. Okay. And if you apply force in this way, about this point, torque will be clockwise. And that is F into separation is L plus X. L plus X. This is a clockwise. Now see what is net torque. F into X anti-clockwise. F into L plus X clockwise. So net value, it is F into L plus X minus F into X. This is now F into L, which is a clockwise net value. So we got same. So here conclusion is that here we are saying torque of a force depends on the origin, means about which point we are calculating. But if you are taking net force on a rigid body is 0, then net torque will be same about any point. That is now conclusion. The examples taken like this is the conclusion is that whenever net force acting on a rigid body is 0, then net torque will be same about any point. Okay, let us see now. Right. The points what we have discussed till now. If net force acting on a rigid body is 0, then net torque is independent of the origin. Okay. Next. Next, I'm going to discuss one more point, that is, if a rigid body is in equilibrium, then net force and net torque both are 0. Okay. If a rigid body is in equilibrium, net force 0, net torque also 0. Let us focus now problems based on torque and equilibrium of a rigid body. Okay. See first problem. A particle of mass m is projected with a velocity u at an angle theta with the horizontal at time t equal to 0. Find the torque due to gravitational force as a function of time, and also find the average torque about point of projection during time of flight. So we have to find as a function of time and also average torque. Let us now focus how to start. It is given oblique projectile. Let us take this is y-axis, or taking vertically up as y-axis and horizontally as x-axis. Then Z will be out of the board. Okay, Z will be, it is outside the board. Normal to board, it is outwards. Right, it is now oblique projectile. Oblique projectile. So shape of the path is, it is parabol. Okay, given velocity, it is u, and angle of projection is theta with a horizontal, it is u, and this is given theta. So now we have to find a torque due to gravitational force. Suppose at one instant, it is now somewhere here, at one instant. Gravitational force mg downwards. It is mg downwards. Now we can see it's a position vector because we have to calculate about a point of projection, right? So with respect to that point, we have to focus now position vector of the point of application of force. I am repeating, we have to take position vector of the point of application of force. That is now R1. Okay. Let me take this as origin O. So take it as A and this point as B. Okay. Then we can write R bar. R bar equal to X I cap. Here X means OB, right? OB is X and AB is Y. X I cap plus Y J cap. Now torque. Torque due to gravitational force. Torque due to gravitational force is equal to R bar cross F bar. R bar X I cap plus Y J cap cross F bar. F bar is now, it is mg. Direction is minus j cap. We have taken y-axis as it is vertically up. Okay, y-axis. It is vertically down. So minus j cap. And in this you can see x value how much? X equal to u cos theta into t, right? Okay. We can see here I cap cross minus j cap. It is minus k cap. J cap cross minus j cap. It is 0. So it is now mg into, in the place of x, I am writing u cos theta into t. Direction I cap cross minus j cap. It is minus k cap. Direction is now along negative z axis. Okay. So according to here, x is x and y. Positive z is outwards. It is now along negative z. Negative z means we can say it is a clockwise. Okay. If you curl fingers, keeping thumb inwards, curl fingers, it is a clockwise. So torque is a clockwise. Or we can say minus k cap. Okay. Right. So we got now torque as a function of time. Now we want to calculate average torque during time of flight. Okay. See now what we can do. Torque is now changing linearly with the time. Okay. If you are focusing modulus of a torque, modulus value, it is mg into u cos theta. This is now constant, right? Into time. It is now changing linearly with the time. And we have learned that whenever a function is depending on, or you can say a function changes linearly, then its average value will be initial value plus final value by 2, right? So initial value when t equal to 0. So torque when time t equal to 0 is 0, right? Next, torque is asking during time of flight. So just before touching ground, when t is a time of flight, it is mg into u cos theta into time of flight. And what is our time of flight? It is 2u sine theta upon g, right? Time of flight. Now average value is given by average torque, initial value 0 plus final value. See how much? G gets cancelled. It is now m into u square sine theta cos theta into 2. It is sine 2 theta, right? That's m u square 2 sine theta cos theta. That is sine 2 theta. Initial value plus final value by 2. So average value is now m u square sine 2 theta by 2. This is average torque during the time of flight. Okay. Like this, we can calculate torque. Let's see how we have taken this one. First, we have taken R bar at xi cap plus yj cap. Next, we got X value. Next, writing directly R bar cross F. Okay.